During the work time today, which will be most of the period, I'm going to hand out your everything. I'm going to ask you to give me your quizzes back at the end of class. I'm going to hang on to those. But anything else I give you, you can keep. But as promised, I just want to go through some stuff that I noticed. This is both for the quiz and for the lab. If you have specific questions on the quiz itself, then once I've handed it out to you, we can talk about that individually. There are a few things that I noticed that either cost you points this time around, might cost you points next time around, or are just things that might help you. They might, even if it's not like this is going to affect the number of points you get, ideally this will affect your ability to learn and understand, and kind of give you some ideas of ways that you could approach the work that we do in the class and getting yourself caught up if there's something that you fall behind with, all right? So I'm going to go through most of this really quickly, and then I will come back to a few of the things. The first is when you do something by hand, write your name really, really clearly and write your full name. I don't even know some of your last names yet. I haven't gotten that far. I know who you are. I know your first names, but some of you I don't know your last name. Even if I've worked with you before, I forget. So give me at least enough that I can find you in the grade book. Okay, so write your full name nice and clearly on all the work that you turn into the bin. The second thing is, and I get that you all are people have their own handwriting and their own style. I'm not asking you to become an artist. I am asking you to the degree it's possible, work neatly and clearly and carefully. And down the road, I'll show you some examples of this. I'm not going to do it today because I don't want to take up too much of your time, but I'll show you what I mean. It is possible for every one of you to be relatively clear with the way that you write and the way that you document your work. So do that. When you turn something in, understand that all I have is a piece of paper to look at. What I want is for you to be learning stuff. I do understand that for many of you, that piece of paper is all I'm going to see. I may not interact with you one-on-one during class as we're working. So make sure that the work that you turn in is really convincing. It should convince me that you know what you're doing. And if you're not sure how to go about that, then come and talk to me. If you talk to me, then I'll know. And I can not only tell you, oh, here's something you can put on your paper that will be convincing evidence that you've learned something, but I'll also, in the conversation, pick up on what you know and what you've learned, and that in and of itself is evidence. As I told you before, the work you do in class is part of the evidence. It's not just the stuff you turn in that counts. It's what I see and what you do in class as well. With anything that we do in this class that involves graphs, which is going to be a lot of it, use graph paper. I provided it for you. I can provide more, but don't make graphs on unlined paper or on paper with just vertical lines. It's not good enough. Use graph paper. And make your graphs big. They don't have to take up an entire sheet of graph paper, but they should also, if you're using with the Match This Motion lab report, we had 5 or 6 seconds of motion and you were only moving 1 or 2 meters. That doesn't mean you use 2 boxes vertically on the graph paper and 6 boxes horizontally. It means you double and triple and quadruple things so that I can actually see what's going on. And if you don't know how to do that, I'm more than happy to show you how you can scale your work so that it's actually visible. I mentioned this before, and there's some hints on the lab itself, but let me be really clear. The labs are not a quiz. You actually had a quiz, the Motion Graphs quiz. That was a quiz. The labs aren't a quiz. What I want you to do with the labs is learn stuff and master stuff. So if there's something you don't know, talk to each other and talk to me. Don't just guess. You don't have to assume that, if you come to me and say, is this right? I'm going to say, I don't know. You should know that. That's that's an appropriate response for a quiz. Because by the time we take a quiz, I'm not gonna help you. But on a lab, I will, and I want you to. If you have talked to me and other students, you'll have a really good idea of what your grade on a lab is gonna be. If it's a 10-point lab, you've talked to me a bunch, and you feel like everything is going really well, then you can expect at least a 9 out of 10, right? If I'm not telling you that doesn't look right, or you need to do this one again, or let me help you with this, then you're doing good. But if you don't talk to me, you won't know that. A couple things in particular that relate to this lab. I did the graphs for you and posted a video for those of you who weren't here. So I was a little bit picky with that because everybody should have gotten those right. And I'll come back to that in just a second because it's possible for you to have gotten those graphs wrong and still gotten full credit on the lab, and I'll explain that in just a second. The other thing is on the lab, it says, make sure to review with your instructor and your classmates as you go. What that means is, I'll tell you if you're right or wrong, because I want you to learn this stuff. And so don't discount the fact that I can tell at a glance how things are going. I can look at your work and be like, you're on the right track, you're doing great, keep going, or let's hit the brakes. There's something you need to figure out. And based on what I think is best for you, I'm either gonna give you not much information, because if I think you're almost ready to figure it out on your own, I'm not gonna like hand feed you stuff. Not because I want you to suffer or struggle, but because you will learn more and it's more rewarding when you figure that thing out on your own. Having said that, I will never leave you hanging. So if I think you can figure it out, but you can't, or if I don't think you can figure it out, then I will give you more. I'll give you as much information as it takes to get you through to having the correct information, because it's not a guessing game. And then let's see, so this is kind of coming back to the graphs. And we'll talk more about this with the next lab. I didn't take off points for this because we didn't talk about it, but going forward, error analysis is something that is actually really interesting and really fun and really important. And for the most part, you haven't probably learned how to do it in a really effective way yet. In the past, you've probably been told, make some guesses about what might have gone wrong. Most of the time, for the first several labs, people are inclined to tell me that there was human error and measurement error and equipment error on the labs. And I already know all those things, and I know that you know all those things. Here's what real error analysis looks like. There's two ways you can think about it. We'll do both in the class. One is a quantitative error analysis. That's what you do when you have replicated data. So if you were to make a prediction and then test your prediction 20 times, then you could come up with an average and do some statistical analysis of your work and figure out, for example, what the standard error and the mean was. You can, that is one way of doing error analysis. Another way of doing error analysis is to critique your predictions based on your tests. And that is more often what we're going to do in this class. And I'll help you get there. So you didn't lose points for this on this lab because we didn't really talk about it. But the idea is, if I have a idea of what I think a motion graph is going to look like, and then I get a motion sensor out, and I do what the instructions say, and my motion graph doesn't look anything like what I predicted it should be, then something's wrong. That's error analysis. And as soon as you know that something is wrong, your job is to try to figure out what. So it's not, I think there was measurement error, I think there was human error, I think there was equipment error. It's, I went back and I looked and I realized that I assumed that the velocity was going to be positive the whole time because it says speeding up. But I realized that I'm speeding up in the negative direction. So my velocity graph prediction was incorrect. It should have been below the x-axis because my velocity was increasing in the negative direction. That's error analysis. You pointed out the mistake you made on your prediction. Or maybe you realize that you made a mistake with the equipment or with the way that you walked. Like, I made my prediction, I tested my prediction. When I looked at my graphs, they didn't match. And then I realized that there was a time period that I was supposed to be standing still, but instead I kept moving at a constant velocity. So that was an error in execution, but it was a specific one. It's not just, I don't know, human error. Like, we all know the general causes of error in data collection and analysis. What I want to know is what actually went wrong. And if you look at your graphs and you have a prediction that matches the actual data to at least a reasonable degree, then your error analysis for that should point that out. And you don't have to think about things like, well, there were little wiggles in the lines. And we know there's going to be wiggles in the lines. You don't need to explain to me why there are wiggles in your lines. You don't need to explain to me that everything was shifted a half a second because you're not perfect at walking perfectly on time. What I want you to say very succinctly is the data that I collected supports my prediction. That's it. That's an error analysis because we don't have any quantitative data for this lab. That's a reasonable error analysis if your results actually support your prediction. And that brings me back to this. I went through the graphs in class, so there's two ways that you could have gotten points for the graphs. One is by doing them right, because you all saw me do them, and so you should have had them right. The other is you could have, in your error evaluation, acknowledged my predictions weren't right, and I know what they should have looked like now. That's okay too. Whether you said, when you did, like, I realized when you did it in class that I didn't curve my position data. I made a straight line because it said constant speed, but I realize now when your speed is changing at a constant rate, I realize now that when speed changes, you get a curved line on a position graph. That gives you full points, even if your prediction was wrong. Does that make sense? You got two ways to do it. Make the right prediction, because I showed you what the right prediction is, or stick with your original incorrect prediction, but acknowledge that it was incorrect, so that I know that you realize, oh, it's not a straight line on the position graph, or the velocity graph doesn't go up and to the right. When you're speeding up, it goes down and to the right. Okay, so this is stuff that's specific to labs in general, but this lab in particular, a whole bunch of you, there were some, kind of one or more of these things turned up. All right, here's some other things. I told you this before, but just as a reminder, when you turn in stuff on Canvas, use that comments box. And I said here, if you turn in late work, make sure to include explanatory comments, but actually anything that you can tell me is useful. Here's what I'm expecting. I'm expecting when you do handwritten work to have a picture turned in on Canvas on time. And I'm expecting to see a hard copy turned into the bin on time. That's the expectation. If I don't see that, tell me why in the comments so that it's written. Some of you may have done all of your work digitally. You may have done the sketches on an iPad, or you may have at home taken pictures of your handwritten sketches and then pasted them into a document. If you turned in all of your work digitally and there's nothing in the bin, that's okay, as long as you put a comment in Canvas that says, I didn't put anything in the bin because you'll be able to read this on Canvas. That's fine. I don't need you to print stuff out and turn it in. I just need to know, because what I do when I grade is I just go through the paper copies. And then I look at Canvas and I look at the comments, and if you didn't give me a paper copy and there isn't a comment on Canvas, then I just don't grade it, because I'm waiting for the paper copy, because I'm assuming that what's on Canvas is a blurry mess that I won't be able to read. So if that's not the case, tell me. And other things too, like you said I could turn this in on Wednesday. You said I could turn this in a week from Wednesday. You told me I could turn this in for full credit in June, and here's the email where you said that. Give me that information, because otherwise what happens is I don't remember. I make so many arrangements with so many people that I just don't remember. And so if you don't give me a comment and it comes in late, I'm gonna take points off. Even if we had an agreement, I will not remember. And all of this is just, these are specific examples of ways that you can make it easy for me to give you full credit. And let me be really clear here. I'm not gonna penalize you if you're doing your job and something goes awry. That isn't my point. But I also know, for example, if I get something that's 2 weeks late and you tell me, I promise I did this on time, that's not making it easy for me to give you full credit. When you turn in late work and you promise to me that you did it on time, you haven't made it easy enough for me to give you full credit, so you won't get it. So just be aware that the more you can do to like make it just abundant, like make those plans with me, put those comments in Canvas, write your name on stuff, like make your graphs big. The more I can look at your work and say, this person understands stuff, did the work, got it turned in on time, the more credit I can give you, okay? And then I'm gonna, like, as we go, there's gonna be little things that gradually become stricter and stricter. So for example, on this, if you made a teeny tiny graph, I didn't take any points off. If you made your graph on unlined paper or just notebook paper, I didn't take points off. But down the road, I will, because I don't wanna have to guess whether your graphs look right or not. I wanna actually see it. So, so keep that in mind. And if you ever are curious, like sometimes we do work in class and basically you're just like scribbling some stuff down and turning it in, and you may just be like, do I need to use graph paper for this? I'll just tell you, like, no, just turn in what you got, it's fine. But a lab, like a 10-point lab, you should assume that you need to be using graph paper for that, okay? All right, that is, that's the lowdown on the general stuff. For the quiz, when I hand it out to you, like I said, I want it back before the end of the period, but if you look at your quiz and you're like, oh gosh, I want to talk about this with you, we can do that. We'll have time to do that today. And then, let's see, the other thing that I just wanted to remind you is that if you wanted to do a retake on the quiz, you need to make an arrangement with me as soon as possible. So, and it's really up to you. Like, I can do a retake pretty much whenever you can. So you can just send me an email and say, Briga, I'm gonna come in, 5th period on Monday to retake the quiz, or I'm gonna come in, Friday during lunch to take the quiz, to retake the quiz. And as long as you had all the work done, turned in on time prior to the quiz, will be fine. You don't need to ask me necessarily. You can just tell me, and then we can do the retake. You're welcome to ask as well. But if you already know, like, the only time I can do it is 3rd period on Tuesday, then just tell me, I'm gonna be here 3rd period on Tuesday, which I guess you all should be here 3rd period on Tuesday. Okay, any questions about that? Okay, I am going to, we're gonna be working on 2 things today. One is tracker, to find some information about an actual cart moving on an actual track. And the other is we're gonna continue working on those basic kinematics problems. And I'm gonna go through some demonstrations of both of those things. So I'm gonna start with a tracker thing, and then we'll go through a problem, and then you'll have time to work. And what I want you to do is spend at least a little bit of class time doing the tracker thing. You won't necessarily finish it, and that's okay. I just want you to at least give it a shot while it's fresh in your brain and while you're here, so that I can help you. And then after you've done that, we'll circle back around to those practice problems. And those practice problems, if you get them done today, great. If not, you can finish them over the weekend. I asked you to turn them in on Tuesday, and I'm gonna give you points based on whatever you turned in on Tuesday, which you all only had a little bit of time to work on them. So you're gonna get full credit on them. It doesn't matter how much you get done for credit. I want you to do all those problems though. So spend the time today during class, and if you don't get done, finish them outside of class, because we're starting the problem-solving part of physics, and the more practice you get, the better. Okay, so here's what we're gonna do with motion analysis. There is a activity posted to Canvas. This will be due on Monday, so we'll have more time to work on it, but again, you should take a little bit of time today to play around with it. Here's our goal. If we have a video of something, we want to be able to figure out that thing's acceleration and velocity at any time in the video. As we get close to the end of motion, it gets harder and harder and harder and harder, and you'll see that. But certainly early on, or in the middle of a video, we should be able to relatively easily determine what an object's speed is and its direction. We can figure out the direction just by looking at it, and how quickly its speed is changing, its acceleration. So I'm going to show you how to do that with the video that I'm actually going to ask you to do. So you'll see me do this with the same video that I'm going to ask you to do. And here's where you might benefit from just writing some notes down, because you might find that there are a couple little things here that if you just jot down a note or two, it'll be helpful. You won't be able to take notes, okay? But there'll be a couple of things that you'll be able to write down that'll be helpful. Okay, so here's what it looks like. The activity is right here, and the instructions for the activity are here, but I'm gonna walk you through the whole thing from start to finish. So it starts with a video, and this is the video right here. When you're doing the work yourself, when you click on it, it should show up and it'll just like play. Okay, there's the video. Isn't that awesome? And what you'll need to do is download it. When you download this, so you click on this little arrow up here, this is one where maybe if you don't know how to download a Google Drive video, maybe just jot this down, but if you already know how to do this, that's great. It's gonna go into your downloads folder on your Chromebook. You'll be able to access it in Tracker. It's not gonna look exactly the way that mine looks though. So just like be aware that, that even though I'm doing the same basic thing that you're gonna do, it might show up in a different spot simply because you have Chromebooks and this is a Windows machine. Okay, and then I'm gonna load Tracker. I'm gonna load the full frame Chrome app, so it's gonna be the same one that you're looking at. And at this point, I'm gonna do something humiliating, which is I'm gonna put on my reading glasses so that I can actually see what's going on, and I'm gonna stick my face up against the computer like Grandpa. Okay, so here's what I'm gonna do. I'm gonna click on this file folder button. Before, you guys were using files that were freely available online. You're not doing that now. You're gonna open the video that you just downloaded. So you're gonna go to File Chooser, you click this button here that says Choose File, and then on your Chromebook, somewhere in there, you're gonna see downloads and like Drive, and I can help you find it. It's not gonna look exactly like mine though. When I click on it, it's just in my downloads folder. And so I'm gonna click open, and then you have to click load. And it will load the file, dun, 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 and there it is. So the way that this file is set up, it starts moving instantly. You can see that's my hand. Cinematic, my acting in this is astounding, I know. My hand has already let go at this point. You can't quite see it, but that's the very start of the motion. This whole thing, right up until it hits this block at the end, is in constant acceleration. As soon as it hits the block, it's different. Once it hits the block, it's no longer in constant acceleration. But you can get a real good idea of what constant acceleration looks like in the time period between when the video starts and right before it hits the block at the end. So to get accurate data from Tracker, we need to put in a calibration stick. Hopefully you all did this on the practice videos that we were using last week. When you put in a calibration stick, it just tells Tracker how big a certain distance on the video is. I put a meter stick here, and the default measurement for the calibration stick is a meter. So if I just stretch it out so that it takes up about the same length on the video, on this frame of the video as this meter stick, there's a meter right there, and it doesn't matter where I put it. So I'm gonna move it out of the way because it's like, I don't need extra stuff. And then the next thing you need to do, and this is a little tricky, is to put in a reference axis. This is the same kind of thing that we're doing when we solve the problems. You put in a reference axis, you tell me or yourself where position 0 is and which direction is positive. You need to do the same thing in Tracker. So when you click on this reference axis, it just puts it in the middle of the screen. You can put this wherever you want, and you can align it however you want. But what you'll find is that if you find a position that's sort of a natural 0, so like I'm gonna use this bumper at the very end, that's the furthest left it goes, I'm gonna say that's position 0. And then see how the track is at an angle? That's the direction that the cart is gonna move. That's my one dimension of motion. So I'm gonna take this, you can see it my mouse turns into a little hand when I put it over the axis. I'm gonna tilt it so that it lines up with the track. It doesn't have to be perfect. That's good enough right there, okay? And now I'm gonna start adding points. And to add points, you click on the track button, you click new, and you click point mass. And then it doesn't matter where you actually click. As long as you click on the same relative position every time. Mel, would you mind letting Levi in? And so I'm gonna click on the bumper, the little spring. This cart had a spring that was sticking out. I'm gonna click on that spring. And so I hold the shift key down and I click, and here's where I'm gonna stick my face right up here. And this is gonna be something you all aren't really gonna be able to see from where you are because it's barely moving. And I'm gonna show you something in just a second that's really kind of cool. So here's what's going on. This graph right here is showing these positions that I'm clicking on along this not quite horizontal line. This graph right here is showing my Y positions. That's along this not quite vertical line. We don't care about this not quite vertical line because our cart isn't moving up and down relative to that line. We only care about this one. But this looks weird, doesn't it? It looks like it's kind of, like if this is a position versus time graph, it looks like it's kind of moving back and forth, and it's not doing that for real. What's going on is it's moving so little, and my screen is so small that I can barely see where I'm clicking. And so I'm not getting it in the right spot every time. And that seems like that's gonna be a problem because there's error. But here's what's gonna happen is as I go, you're gonna see that line, the scale is gonna change. I'm not looking at it, by the way, I'm just clicking. And as this cart starts to move more and more and more, the scale is gonna change such that those initial errors are basically gonna disappear. And you'll start to see a smooth curve that goes down and to the right as this cart accelerates in its negative direction. It should have started with a velocity of 0 because as I let go, it wasn't moving. And as it moves down the cart, its velocity is increasing, which means the distance it travels every second, every part of a second is increasing. And I'm still not looking, but how does my curve look? Is it starting to look like a pretty smooth curve? Yeah, this is what you should see as well. Smooth curve, smooth curve, smooth curve. Yes?
Do we have to do this in the intervals of time that you're doing it, or can we speed up the process by doing like 1 second intervals? Because I don't really want to click it 200 times.
So the answer is there's 3 answers to this. Number 1, if you can find the information that you need, I don't really care. So it's fine with me if you just click once or twice. And if you can figure out what you need to find out, that's great. You'll see I'm not going to click the entire time that it's moving. I'm only clicking now at this point because I'm talking. The second thing is you should, if you need to, be able to do it a bunch of times, because there might be some times when you won't get an accurate picture of the motion unless you can click at least 20 or 30 times. So get used to being able to do that. The third thing is, I don't know if you can just skip. You can play around with it and see. I don't know exactly how it works. I'm not going to demand that you put 200 points in. What I want is for you to be able to find the information. So, all right. Then the next step is I'm going to right click on this graph. Now, this graph, sorry, let me just show you this lower graph here. This is my y-axis positions, and it's jumping up and down, but actually it's not really. The scale here is so small that everything is within 1/10 of a millimeter of the same line. It's on the ramp. That's what this data is telling us. We do not care about this data at all. We already knew it was going to stay on the ramp. We knew it wasn't going to bounce up into the air or sink down into the ramp. This data is showing it move to the left and slightly downward along the ramp. Okay, this is along our one-dimensional x-axis, which is tilted with respect to the ground. So this is the data we want to analyze. So here's another thing that you might write down, is that you're going to analyze just one set of position data at a time. Since this is moving one-dimensionally, we only need to analyze this data. And the way to do that is you right-click on it and then choose Analyze. And it'll pull up a graph, and you can see, like, there's some errors in there. It isn't perfect, but by and large, it's a pretty smooth, frowny face parabolic curve, which by now I hope you recognize as being associated with a position graph showing constant negative acceleration. And then if we go to this, there's a button here that says Analyze. Again, this is something that might be worth writing down. And then you click on Curve Fitter. This is a parabolic curve. Parabolic and quadratic are the same thing. Parabolic refers to the shape of the curve. Quadratic refers to the type of equation. So a quadratic equation generates a parabolic curve. Our position data should be quadratic because it's going to match up with that equation that we looked at the other day, where position is 1/2 acceleration times time squared plus initial velocity times time plus initial position. So I'm going to click parabola here, and then I get some stuff down here. And this is where we're going to get our information. So I'm going to take a quick screenshot of this. And let's look at it a little bit more closely. Okay, so here's what the program told me. Okay, I gotta put my real glasses back on. And here's what I told you all the other day, that the generic equation, the generic quadratic equation that will generate a parabolic curve looks like this. Y equals ax squared plus bx plus c. And then I told you that this matches up with one of our kinematic equations. It matches up with this one. X equals 1/2 axt squared plus v naught x t plus x naught. The initial position is the c parameter. The initial velocity is the b parameter. And 1/2 of the acceleration is equal to our a parameter. That means that this a parameter is 1/2 of this object's acceleration along that axis. And we have the big A parameter. We're looking for acceleration. So what we do is multiply both sides by 2. And we get our acceleration is gonna be equal to 2 times that big A parameter. Our initial velocity and the B parameter are the same. Our initial velocity will be equal to that B parameter. What I want you to be able to use Tracker to do is find velocities and accelerations. Here's how you find the acceleration. Look at this number right here and multiply it by 2. This is a weird number because, first of all, it's got this plus or minus. What in the world does that mean? That's indicating that this is its best guess, and it thinks it's within 0.007 of the correct answer. We don't have to worry about that. This, by the way, is what a quantitative error analysis looks like. But just ignore that. The real number that we care about is this, and we can round it, because this isn't perfect, negative 1.2. What about the e to the negative 1? That's scientific notation. This number is really negative 1.2 times 10 to the negative 1, which means we just move the decimal point. It's negative 0.12. That is our big A. Our acceleration is going to be 2 times that number, so it's going to be 2 times negative 0.12, which is about negative 0. And I'm going to round it even more, 2.5, because quarter. It's a quarter of a meter per second squared. That's a little bit wrong, but who cares? It's going to be good enough. That is how quickly this thing's speed is changing. Every second that goes by, it's going about a quarter meter per second faster down the ramp. What about my initial velocity? My initial velocity, so again, we can ignore this plus or minus piece. It's negative 3.4 times 10 to the negative 2. So that means I move my decimal point 2 to the left. So that's going to be negative 0.034. That's a real small number. That's basically 0. Our initial velocity is 0 meters per second. And if you think about it, we already knew that. We knew it wasn't moving. Right as I let go, it wasn't moving yet. It took time before it started moving. So in that very first frame, the velocity is 0. If we looked a second into it, I would expect that the velocity would be about a quarter meter per second, because it's accelerating at a rate of a quarter meter per second every second. So that is going to take you all some practice. I get that for some of you this is pretty intuitive. For some of you it's intuitive, but you may not remember how to do it. And for others, that maybe didn't make a ton of sense. So just understand that what my expectation is that you're going to practice this several times. I'm going to give you, you'll use this video today, but we'll use other videos in the future. We'll just keep practicing it. Ideally, those of you who are really struggling with it will take some time to practice on your own with the videos, the sample videos that are available, so that you can really get good at it. Your goal should be to be as fluent as I am in Tracker. You get a video, you figure out how fast something is moving, you figure out its acceleration. That simple, okay? All right, I'm gonna pause there for just a second.